So now we come to bending. At first sight, it's not so much a force as it is a phenomenon, both vertically and horizontally. And it's the result of tension and compression, as we'll see in a moment. We see bending in nature when it is essential for a structure to withstand loads from almost any direction. Let's look at a blade of grass. If the wind blows, it bends. That means that the front side is compressed and the back side is stretched or in tension. So even a simple blade of grass has to be designed to contend with that. Well, what is even more interesting is that the grass never knows which way the wind is going to come from. So it has to be able to resist that all the way around it. That is why the cross-sections of grasses and twigs are so beautifully symmetrical. It's the only possible response to the vagaries of nature. In the man-made world, the best vertical columns are circular ones. The only problems they have is that it is difficult to fix things to them. That's why we often use compromise sections, like the simple square post that holds up a stop or parking sign. For horizontal members, the situation is a bit different. In general, the bending is only going to be in one direction, down. So we find that the ideal shape for a beam is not circular, but rather rectangular or eye-shaped. Mind you, bending is not necessarily bad news. Lots of things can bend and not break. But a problem comes when we connect things that can bend with things that don't like to bend, such as windows and plaster. They crack. So really, bending or deflection is more of a nuisance to us rather than a problem.
There is a product of bending that does produce additional forces. It's called bending moment, and it's the simple action of the lever arm. We see it best in the action of the teeter-totter or seesaw. Here you can see that even I could be tipped in the air by somebody much lighter than I am if I sit closer to the pivot. It would vary, of course, for different combinations of people, and it doesn't take long to figure out that there's a relationship between the weight of the person and the distance they are from the centre.
And the formula is very simple. You just multiply the weight by the distance from the pivot for both sides. If the answer's the same, you balance. If one is bigger, that's the side that goes down. So the greater the distance the weight is from the fulcrum, the greater the force it can exert.
And if we don't take that into account when we design our structures, the consequences can be surprising, to say the least.
Let's look at kitchen cupboards. If the designer has made a mistake or been careless, you might have a set of drawers right next to the hinged side of a cupboard door like this. If the drawer is accidentally left open a little, the door comes around like this. And if you push on the door, you can put half a ton on that hinge and break it with little effort on your part, just because you've left the drawer open a bit. You see the same thing in the drop-down flap on some desks. If it sticks out too far and you lean on it, you can snap it right off. And all because of the phenomenon of bending moments that we demonstrated with the teeter-totter. Now I can guess what you're saying. We don't usually build teeter-totters into our buildings. Well, just look at these illustrations. Here we see a teeter-totter being held up by a strong man that is bending under the weight of the two people on the ends. Now look at what happens if we invert the drawing. Our teeter-totter has become a beam with our heavyweight champ doing a handstand in the middle. If we move him closer to one end or the other, we increase the load on the person holding up that end. He will have to be stronger to keep his end up. An example of this phenomenon can be seen in this parking garage. The cars move, which results in the columns being loaded differently at different times. Not only that, the cars might be parked all at one end while the other end is empty or unloaded. So the columns have to be designed to contend with the worst situation. But there are limits to strength. The force on the structure, whether it's compression or tension, produces stress. The stress is the intensity of the force on every unit of area. The larger the force, the greater the stress can be. The structure responds by changing its shape a bit, by deforming. That's part of being elastic. And we call the actual amount of deformation the strain on the structure. The greater the stress, the larger the strain. Now, there are limits to both. Even elastic materials can't deform endlessly. An elastic band will snap if the stress and strain are too great. A ruler will break, as a rule, that is. So, every structure we design has to take bending moments into account. For instance, with this aircraft, too much load on the end of the wing and it could break. On the ground, it's the fuselage that's holding up the wing. But interestingly enough, when the aircraft is in the air, the situation is reversed, and it's the wing that's holding up the fuselage. Now, this is important because sometimes what was in tension on the ground could become compression in the air. So, too much stress of the wrong sort on any structure could cause it to fall apart unless it's been designed to take it. To review then, the forces of shear, torsion and bending are really just expressions of compression and tension. And it is compression and tension, push and pull, that governs so much of our world. Without being aware of their effects, we'd have a hard time designing a structure that would stand up, let alone fly. In the next programme, we shall begin to look at the design of some of these structures. Home, James.
It's a heck of a day for this one, Brian.
The British way.
Oh, you're right.
Okay, what we're going to do is just taxi out here. Now, I'm steering it with my feet right now.
Okay.
What we're going to do is put your hand on the control column.
Yes.
As we go down the runway, we'll just lower the nose a little to the floor. Adjust it. The only other thing that you might have to control is that if a wing drops either side, you just have to adjust your with the tail.
Terrific. Just like driving a car.
Just about.
Fantastic.
A little bit easier. Far less things to bump into.
That's true. Not much traffic around up here.
No, no.
What's our ETA for Moscow Red Square?
Moscow Red Square. No, thank you. I got it.
While I'm up,